Hey. All right, today we are going to talk about infinite limits. And really, what we're doing when we talk about infinite limits is we're dealing with vertical asymptotes. Okay, so this is lecture 1.5, and we're going to do example problems from page 84 in your book. All right, so just a real quick aside, if you are not my student, the book that I am using is Calculus 6th edition, Larson, Hostetler, Edwards. You can get these really cheap. Sometimes even like $1 a piece. All right, so they're pretty old. Okay, so I want to draw a graph here. And let's just draw a graph that's got an asymptote. So, an asymptote, hopefully you remember from Algebra 2, pre-calculus, we use a dash line. So let's say that this is at the x value a. All right, and I've got a function f of x, let's say it's going down from the left. It can approach the asymptote but never get quite to it. And let's say from the right, looks something like that. From the right, it approaches but can never get to it. So we call this kind of asymptote a vertical asymptote. A lot of times I will just do this instead of writing all that out. And so let's take the limit as x approaches a from the right of f of x. Well, you can see it just goes on up forever. It never crosses that asymptote. It's going up forever. So that would be infinity. We can even, if you want, write a positive infinity, but it's infinity. You don't have to put the positive. If we take the limit as x approaches a from the left of f of x, here it's going down, 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 so that's negative infinity. All right, just never crosses that asymptote. So this is really just a special kind of discontinuity. So a vertical asymptote is a discontinuity. So section 1.5, we're still dealing with a discontinuity. Okay, let's do a couple of examples. And these functions would have a vertical asymptote in. Let's say we want to look at f of x is equal to x plus 5 over x plus 3. All right, there's potentially, or there is a vertical asymptote at x equals negative 3, because that's what makes the denominator 0. That's where you have vertical asymptotes, where the denominator is equal to 0 but the numerator is not. So let's take the limit as x approaches negative 3 from the right of x plus 5 over x plus 3. All right, from the right, so we're talking about negative 2.999. So that's basically, though, 2. And on the bottom, you're going to have a small positive because negative 2.99 plus 3 would be a small positive. So 2 over an incredibly small positive, let's say like a trillionth, just approaches infinity. Now let's take the limit from the other side, negative 3 from the left. I'd have x plus 5 over x plus 3. That's again going to be 2, But from the left, it's like negative 3.0001, right? 0001. So that's over a small negative. So that would be negative infinity. So that's kind of like the situation here in this graph. All right? That's not equal. So the limit does not exist. However, you are able to give, even though you know the limit doesn't exist, you are able to give yourself some information about this function. And that is, if you're approaching from the right, the graph is going up forever. And if you're approaching from the left, the graph is going down forever. So although the limit doesn't exist, you get some information about this function. All right, let's try another one in a similar way. Let's say we have f of x is equal to 2 over x minus 5 all squared. Okay, so where could we have where are we going to have a vertical asymptote? All right, that would be at x equals what? X equals 5, because you plug in a 5, that's going to be 0 on the bottom. So let's take the limit as x approaches 5 from the right of 2 over x minus 5 all squared. All right, and that is going to be 2. From the right, it'd be a positive squared, so that'd be a small positive. So that's positive infinity. And then we'll look at the limit as x approaches 5 from the left of 2 over x minus 5 all squared. Now inside the parenthesis, you'd have a negative number, right? But you square it, and it will be positive. So still a small positive. Now the limit still doesn't exist, because infinity is just a concept. But you get some information about the nuance of the function. Okay, so you can say that the limit, it doesn't exist, but you can give more information if you say it approaches positive infinity. So if this graph has a vertical asymptote at 5, and it could be something like each direction, so you've got something like this. From the left and from the right, they both approach, they both go up forever, both sides. Okay, so I've already shown you kind of how you do it, but let's do some examples where we find vertical asymptotes, because that's what a lot of the homework is. It's just finding vertical asymptotes, which you should have done in both Algebra 2 and Pre-Calculus. Okay, so a vertical asymptote exists where f of x approaches infinity or negative infinity. And what you want to do is look for places where the denominator is equal to 0. Okay, not everywhere where the denominator is equal to 0 is an asymptote. It could be a hole. Okay, so our first example is find the vertical asymptotes of, can be more than one, f of x is equal to x squared plus 1 over x squared minus 1. All right, well, I can factor the denominator. So let's do that. That factors into x plus 1, x minus 1 times x minus 1. Can't factor the numerator, can't cancel anything out. So what numbers would make the denominator 0? Well, that's at x equals plus or minus 1. Okay, both of those would be asymptotes. So two vertical asymptotes on this graph. Let's find the vertical asymptote of f of x equals cosecant x. Okay, so cosecant, it would be helpful to think about that as just 1 over sine x. Where is sine 0? Well, you can take a look at your unit circle. You know that sine, remember sine, it's cosine then sine. Sine is 0 at 0 and at pi. So it's multiples of pi. So it would be the vertical asymptote occurs where sine equals 0. Sine x equals 0. So that's at x equals 0. That's the first one. Pi, 2 pi, 3 pi, etc. One way to say this, to shortcut that, and not because it goes on infinitely, also in the negative direction, right, would be 0 plus pi times n, where n is an integer. Okay. So vertical asymptotes exist where the numerator does not equal 0 and the denominator is equal to 0. So you have the form non-zero over 0. If you have that, you got a vertical asymptote. Okay, let's do some examples from the book. So the first one is example 10 on page 84. All right, so there we want to find the vertical asymptotes, if any, and we have f of x is equal to 4 over x minus 2 all cubed. Okay, so where do we have a 0 on the bottom? Well, that's we have a va at x equals 2, right? Just eyeball that joker. How about example 12? We have g of x equals 2 plus x over 1 minus x. Well, this is another one that you can just eyeball. What makes it a 0 on the bottom at x equals 1? Okay, example 14. We have f of x is equal to negative 4x over x squared plus 4. Can you plug any number in for x that would make the denominator be 0? And the answer is no, because when you square a number, it automatically makes it positive. Okay, so the denominator can never be 0. So we have no vertical asymptote. All right, let's look at 16. So we have f of x equals secant pi x. Well, let's look at this. Let's change this into cosine. So that'd be 1 over cosine pi x. So we know from the unit circle that cosine is 0 at pi over 2, 3 pi over 2, and then every pi radians, in the northern and southern hemisphere here. All right. So the North Pole and the South Pole. So multiples of that. So where does it equal 0? So we have a vertical asymptote at x equals, well, the first one would be 1/2, right? If we plug in a half for x, we'd have pi over 2, and then cosine of pi over 2 is 0. Then the next one's at 3 pi over 2, so 3/2. Then 5/2. And it goes like that. Okay, so the way we could say this would be at the vertical asymptotes occur at 1/2 plus, and then 2/2 or pi times n. Or excuse me, just n, because we've already got the pi in there. So where n is an integer. All right, so you just add 1. 1/2 plus 1. 1/2 plus 2/2 is 3/2. 3/2 plus 1. 3/2 plus 2/2 is 5/2. Okay, and then you could go the negative direction also. Okay. Let's look at 24. So still doing the same thing. G of theta is equal to tangent theta over theta. Well, you're going to have a vertical asymptote at theta. Let's change this into sines and cosines. So G of theta is equal to sine theta over cosine theta. So that's changing tangent into sine and cosines over theta. And now if you multiply that top fraction by 1 over theta, you can bring that theta up a level. So that would be sine theta over theta cosine theta. So the denominator is 0 when theta is equal to 0. So we have a vertical asymptote at theta equals 0. And then where's the first place cosine is equal to 0? Well, that's at pi over 2, right? So pi over 2 times cosine of pi over 2, it'd be pi over 2 times 0, which is 0. So the places where cosine is 0. So 3 pi over 2, 5 pi over 2, etc. So we could shorten this by saying 0 plus pi over 2 times n, where n is an integer. Because we're adding 1 to that every time. Okay, so if n is 1, 2, 3, 4, negative 1, negative 2, negative 3, negative 4, then that would do the trick. Okay, let's look at 26. There we have, let's see, just reading the instructions, it says, determine whether the function has a vertical asymptote or a removable discontinuity at x equals -1. Okay, I'll show you how to do that because it's not always a vertical asymptote. So in this case, we have f of x is equal to x squared minus 6x minus 7 over x plus 1. Okay, let's see if we can factor that, and I'm gonna make a guess real quick that one of the factors is x plus 1. So how about x minus 7 times x plus 1? Let me FOIL that out. X squared minus 6x minus, so that does it. We could cross that out. So we would have a potential vertical asymptote at -1. That would make the denominator 0, right? But since it crosses out, there is a hole. So if you can factor it out, you can cancel it. That's a better way of saying it. If you can cancel it, then it's a hole. Because x plus 1 cancels. Sometimes you will have more than one factor in the denominator. One of them will cancel and one of them won't. And the ones that won't are vertical asymptotes. The ones that do cancel are holes. Okay, so let's write that down as a note, okay, so that you don't have to remember what I just said. If you can factor and cancel the denominator, it is a hole. And a hole is a removable discontinuity. So we have a removable discontinuity at x equals -1. Okay, let's do a couple of fancier ones. And then you'll be ready for the homework. So example 34. So we're on page 84 still. We want to take the limit. So this time it just says find the limit. Okay? So nothing about a vertical asymptote. Just find the limit as x approaches -1/2 from the right of 6x squared plus x minus 1. So really we're just giving you more practice with limits here. And it needs more work. So if you plug in -1/2, you're going to get a 0 over 0. So what would we do with these two trinomials? You're going to try to factor and see if anything cancels out. All right. You may have to think about it a little bit, but 1 only has one factor, so I know that I can just put a 1 and a 1 there. Let's see, 6b, 3 times 2, let's see, 3x, 2x, let's see if we can get that to work. About minus plus. Okay. And then, let's see, that'd be 6x squared plus x. Yeah, that works. Okay, and then on the bottom, I know that I can do a 3 and a 1 because those are the only two factors of 3. Let's try a 2x and a 2x. So I'm going to do a plus on one of them because that would make that cancel. Let's see if this works. So 4x squared minus 6x plus 2x, that'd give me minus 4x and then minus 3. So we can cross that out as long as x does not equal -1/2, right? So we would take the limit as x approaches -1/2 from the right of 3x minus 1 over 2x minus 3. We can go ahead and plug in a -1/2 there. And after you do that, you would get 5/8. Okay, so you know there's, in this particular case, there would be a hole because it canceled out. We have a hole at -1/2, so that's a removable discontinuity. And then you would have a vertical asymptote where if you set 2x minus 3 equals 0, 2x equals 3, so x equals 3/2, we have a vertical asymptote there. It didn't ask you to do that, but because 2x minus 3 didn't cancel out, 3/2 will give you 0 in the denominator. If it did ask you to find it, that's how you would do it. Okay, and the last example of the day, be 42, and we just want to find the limit. So we have f of x is equal to x cubed minus 1. Well, let's go ahead and write it out as we're determining the one-sided limit. So the limit as x approaches 1 from the left. So we're taking the limit as x approaches 1 from the left of x cubed minus 1 over x squared plus x plus 1. So I picked this example for a reason. You see this and you think, oh, I got to factor a cube. But look at the denominator. Everything is positive. If you plug a 1 into the denominator, so on top you're going to have a 0 if you plug a 1 in. On bottom you'd have a 3. So the limit, the answer is 0. All right, so there you go. That's just a straight up plug-in limit, and so always do that before you start doing a lot of work. Okay, the homework from this section. A lot of this homework is really short. It's page 84. You can do 1 through 5, so do both the odds and evens on 1 through 5. 9 through 43, but the odds only. And the odds are in the back of the book, so you can check your work. And then 47. All right, and just taking a look real quick at 47. So it says, on this one, you're just going to take the limit of that function as x approaches 25 from the left. So, don't let the fact that it's a word problem there confuse you. All right, so there you go. And I will talk to you on this solutions video for 1.5.